Okay, great. Well, I'm Pete Bartram, and I've got my colleague Karen with me today as well, and we're both from Lumi Space. And we're going to give an overview, or I'm going to give an overview of the challenges that we've put together for this hackathon. So in terms of what I'm going to talk about, I'm going to give a brief overview of the concept of sustainability in space, and why, as a civilization, we need to change some of our practices going forwards. I'll then give a bit of an overview as to what Lumi's approach is to ensuring future sustainability in space. I'll then give a quick overview of the challenges that we've set for this hackathon. And then finally, I'll do a bit of a dive into the data. So I've put together a Jupyter notebook. And the idea of this is just to save some of the legwork with loading the data into Python and plotting it. So sustainability in space. The use of space is fundamentally a good thing. The technologies it enables improve all of our lives. So, for example, communications, a lot of this is done through space. Also GPS, navigation, food delivery, all these things rely on space-based technologies. But also other things that you might not think of. So monitoring of the sea levels in the ocean, the ice caps, forest fires, all of these things are enabled by space-based technologies. So space-based technologies are fundamentally a good thing. And as we move forward into the future, we want to make sure that we and our ancestors are able to carry on using these space-based technologies to improve their qualities of life, or the qualities of their lives. So if we look back at on this cartoon in the 60s, or the late 50s, we can see there was basically nothing in space. Then the space race happened, and we just indiscriminately launched things into space, and this created a lot of space debris. And you can see by 2005, there was more debris, 2018 even more, and looking into the future, there's going to be even more debris to deal with. So the question is then, how much debris is there in space, and how many satellites are there? So there's on the order at the moment of 10,000 satellites in space, although that is rapidly increasing at the moment with the mega constellations. And in terms of space debris, it's split into two categories. So debris that is greater than 10 centimeters in size, and debris that is smaller than 10 centimeters in size. So in terms of debris that's larger than 10 centimeters, there's estimated on the order of, say, 100,000 pieces in orbit. And then when you look at debris smaller than 10 centimeters, you're getting more towards estimates of 1 million pieces of debris. So you might be thinking, okay, so 1 million pieces of debris, that sounds like a big number, but then space is quite big. What's the problem? If there's 1 million cars on the surface of the Earth, they wouldn't necessarily collide. It wouldn't be an issue, given that there's 35 million cars in the UK. So that makes sense, but it's more complicated than that, and that's because of the velocities that these objects travel with. So as a satellite goes around the Earth, it travels in low Earth orbit at 7 kilometers per second. And the volume that is swept out by this satellite as it orbits around is vast. And then if you multiply this by the numbers of satellites, that means that interactions or close encounters are fairly common between these objects, and therefore this means that collisions are also more likely. Now, this problem is compounded by the fact that although space is vast, we don't actually use very much of it around the Earth. So there's two main regions that are defined in terms of their altitude. So the first is low Earth orbit, and this is up to about 1,000 kilometers. This is used for things like Earth observation and communications. And then there's the Geosynchronous Belt, which is further out at 44,000 kilometers. And this is where the satellite stays over the same point on the Earth. So this is a very useful orbit. But what this means is that not only are these big volumes of space being swept out, but the actual orbital shells where these satellites are relatively thin, and that means they're all in a smaller volume and are more likely to experience collisions. So in terms of collisions, I just included this plot to give you an idea of what these collisions look like. So as I said, the orbital velocity is about 7 kilometers per second in LEO, and that means that you can get collisions of up to 14 kilometers per second for objects that are traveling in opposite directions. Now, if you consider this is about 20 times the velocity of a bullet coming out of a gun, and then you consider the kinetic energy is proportional to the square of that velocity, and you can quickly see how collisions become a problem. So in these two pictures here, on the left, we have the radiator of the Space Shuttle Endeavour, and you can see that a hole has been punctured in it here. And actually, it's believed that this was caused by a fleck of paint traveling at these speeds. And then on the right-hand side, we can see this is a crack in the window of the International Space Station cupola window, which again is believed to have been caused by a fleck of paint. Luckily for the astronauts, it's quadruple glazed, but still it'd be quite scary to be up there, I think. And this gives you an idea of the damage that a fleck of paint can do. So if you then consider the masses involved of a satellite-on-satellite collision, where these can be on the order of, say, a ton or 2 tons, then you can quickly see the amount of damage this is going to do and how these impacts could break apart satellites and cause vast amounts of space debris to be produced. So that's really what this plot here shows. But before I get into that, let's just look at the red on this plot. So the red on this plot is, well, along the x-axis we have time, and on the y-axis we have the number of objects. And this is in low Earth orbit. So the red on this plot shows the number of payloads in space. So this is the good stuff. This is what we get utility from these satellites. And everything else on here is space debris, so a byproduct of us putting the payloads here into orbit. So you can see that there's a big increase in the number of payloads going up, but there's a bigger increase in the amount of space debris on orbit. And you'll probably have noticed that the green, well, the debris, there's 2 main regions where it steps up quite sharply. So the first one is here in 2009, and this was a Chinese anti-satellite test where they launched a kinetic impactor into a weather satellite as a weapons demonstration. And at the time, this produced so much debris that it actually doubled the number of pieces of debris of 10 centimeters or larger on orbit at the time. And that's just a single collision. Now, the second jump up here that we see was later, I think in 2011, and this was the now famous, 2009, the now famous Iridium Cosmos collision. And this was a collision between 2 satellites, one of which was derelict. And again, this caused an increase in the number of pieces of space debris by about 2,000 pieces greater than 10 centimeters. So you can quickly see how rapidly very few number of collisions can lead to large numbers of pieces of space debris that then other satellites need to avoid, need to perform maneuvers to avoid, and also these objects need to be tracked. So yeah, additional pieces of space debris is just very bad for the whole chain in general. And if you take the creation of space debris by collisions of satellites to the extreme conclusion, then you end up with something that's known as the Kessler syndrome. So this chap on the left is Donald Kessler, and he wrote what's now the seminal paper on the right-hand side that has led to this term, the Kessler syndrome. And he was trying to look at how many objects you could have in a given orbit before they would collide. And what he found is that there is a critical number of objects that you can have in orbit, and after that point you rapidly get an exponential increase in the number of pieces of space debris. And this is caused essentially by chain reaction. So if 2 objects collide, produce 3,000 pieces of debris, these 3,000 pieces of debris go on and collide with 3,000 other objects, you can quickly see how you end up with an exponential growth problem here. And we don't know if the number of objects in orbit is past the threshold for the Kessler syndrome. It could be that we've already exceeded it, and It's just taking a long time for this chain reaction to start at the beginning. But once it does start, then we could be in real problem, could be having real problems, because depending on the orbit, it could take somewhere on the order of 25 to 100 years for this debris to decay. And during that period of time, we're completely unable to use that particular orbit. So you could end up in a situation with this syndrome where essentially you couldn't launch anything else into space, and essentially you would be trapped on the surface of the Earth in terms of space exploration as well. So Kessler syndrome is definitely one to avoid. And yeah, it's a key part of sustainability in space, which is something that we're working towards at Lumi. So our approach at Lumi is if you know the state of your satellite, so the position and velocity of your satellite accurately, then you can predict out over a relatively short time horizon, say up to a week, where that satellite is going to be. And if you have the same information about all the debris, you can propagate the debris as well, and then you can compare their orbits to see if these objects are going to collide during that time frame. And if they are, then for the active satellites, that means you can perform collision avoidance maneuvers to get your satellite out of the way, and this will stop the buildup of space debris in space and hopefully work to prevent the dreaded Kessler syndrome. So Lumi's approach to this is to use the most accurate ranging technology out there, which is satellite laser ranging. And the idea is that we shine short laser pulses off of the body of the satellite, and you can measure the amount of time that it takes to travel to the satellite and come back to the ground station. And then by knowing that, you can calculate the range that the satellite is from the ground station. This then means that with this ranging data, you can fit an orbit to this, and then you can do all of these propagation things that I just mentioned. So that is Lumi's approach to helping solve the space sustainability problem going forwards. And that just leaves the challenges and the dive into the data. So we have two challenges that we've laid out, and the intention is for them to both be quite blue sky. We're interested in hearing what ideas you have, and yeah, we're just interested in hearing what your opinions are about both of these challenges. So the first challenge is the more technical one. So we're going to provide data from some orbits of satellites. Not quite sure on how many, it could be 2, it could be 50, but a number of satellites. And the challenge is to create a visualization tool to present this space situational awareness data. So this could involve plotting the orbits of these objects. It could involve looking at conjunctions between these objects and how you would display these in a user-friendly way, but also thinking about how an end user would want to interact with this data and what information should be useful to them. So we have provided data, and there's some Python code for extracting the data to make it easy to plot. But if you're not so technical but still wanted to get involved with this challenge, then that's also fine. It could equally be, some mock-ups in PowerPoint of how you think this tool should look and what features it should have. So I think don't necessarily be put off if you're not interested in looking at the data for this one. And the second challenge really is even more blue sky than the first one. So we want you to think a bit about what the future of sustainability in space looks like. So what challenges are facing the industry in the future? So there's some examples here that we've put down. So exponential satellite launch rates, future materials and pieces of debris, but also future uses of space. You might want to think about, for example, what trends are going to change on the Earth, and what way would space technology be used to enable that, and how would that affect the space environment. So very, very blue sky. And also as kind of a stretch goal, combined with challenge one, in what ways would it be useful for the tool, the visualization tool, to be adapted to to manage those future challenges. So I think at that point, I'll ask if anyone has any questions, and if not, then I will get into the Jupyter Notebook. Take that as a no. Okay. Okay, so we will be providing data, as I said, for this challenge, and also be providing this Jupyter Notebook, as I already mentioned, just to kind of save you the legwork of extracting the data from the JSON files and kind of figuring out what's there. This is meant to give you kind of a leg up to be able to hit the ground running with this. So at the top, there's just an overview of the two challenges that I've already mentioned, so I won't go into that again. But then in this first cell here, we're accessing the data. So this is stored on file in JSON file format. Now, there are two files for each satellite that we're going to be providing data for. So for example, here there is two satellites. There's Globalstar here and Envisat here. And there are two second halves of the name. And the first is here is state, and the second here is passes. So state gives you orbital data. So this will give you the position and velocities of the satellites, and also the attitude of the satellites in terms of your pitch and roll. So if you want to visualize the satellites, you can. And then the second is passes, which I'll get into a bit further down. But essentially, this is data taken from the point of view of a ground station on the surface of the Earth as the satellite goes above. So if you wanted to do some work with ground station related data, then this passes.json would be the files to look at. So as I said, we have Envisat above. So this is Envisat. It's about the size of a small bus. And is a piece of, now a piece of space debris. So yeah, this cell is just loading the data from the JSON file into a dictionary for access. So we can see here that this orbit dictionary is created, and then the keys to this dictionary are printed to show what's in there. So you can see in here we have, as I said before, the position, velocity, and then your pitch and roll, and also time in here as well for plotting. And just as an example of what the orbital data would look like, we can see here is a plot just where this is plotting this fake Earth body here, and then you can plot the satellite's orbit around the Earth like so. Okay, and then the second part here is the ground station pass data. So there's data here from a number of passes. I think it's about 6 or 7 over 2 ground stations. The first is Graz in Austria, which is an SLR station, and also Hurstman Zoo here in the UK. And you can see down here information about the 2 ground stations, so the latitudes and longitudes of them. So yeah, it might be worth having a look at where that is on a world map and seeing how the satellites pass overhead. And then the pass data is loaded instead into this ground station object, which is then indexed for the number of the ground station and then the key passes. And then you can index the number of passes. That will be 0 to probably about 7 in there. And then again, printing the keys here so you can see what is in the dictionary here. So in terms of the ground station passes, you can get an azimuth and an elevation. So if you imagine, if we look here at this coordinate system here of the ground station, then you would get an azimuth and an elevation, which would show you the passage of the satellite overhead. And that would look something like this, where you have the azimuth here on the continuous axis and then the elevation here above the horizon. And I've included a Wikipedia page here to go and look at, which goes into a bit more of an explanation about ground station coordinate systems. Other things that might be of interest in this data also is this W here, which is the satellite rotational angular velocity. So you might want to see how fast the satellite is rotating on its axis, for example. And then there's a series of useful vectors in here. So, for example, the position of the ground station in inertial space, position velocity of the spacecraft, and then also the range here between the satellite and the ground station as measured by satellite laser ranging. So perhaps there's some ways in there that you'd want to plot this range to show what's going on there in the tool. And finally, as I said, in addition to the orbital data, so the orbit around the Earth, there's also the rotation of the satellite about its center of mass. This is known as the attitude data, and this is described in terms of, well, several ways, but described here in terms of yaw, pitch and roll, which you can go to this Wikipedia page if you're not familiar with. But essentially, we can see here plotting the yaw, pitch and roll. Essentially, this is the pitch, this is the roll, and then this is the yaw. So what this means is that the satellite is in a flat spin rotating about essentially its z-axis. So again, you may want to consider plotting some attitude data as well to see what's going on there. And although this is in the passes dictionary, there is attitude data available for the whole orbit rather than just for a ground station pass. So if that was data that you're interested in plotting, then that is in the main orbits dictionary instead. So that is it in terms of the Jupyter Notebook. I will stop sharing. So yeah, if anyone has any questions, I'll take questions. If not, then I guess good luck with the challenges, and we're interested to hear what you come up with and see what you come up with as well. Okay, so there is a question in the chat from Giorgio. What kind of submission format do we expect? Well, given that it's a hackathon, the idea is to put something together quickly. So, I mean, maybe mock-ups of what you think this tool could look like, I think would be probably the quickest way to do it in the time that you've got. Maybe some plots of the data as well in there would be useful. I'm not quite so sure for the second one. Do you have any thoughts about that, Karen?
I might need to lean on Fedor a bit, but is there going to be presentations? Are we, from our point of view, we'd like to kind of see some slides perhaps from the teams and have the information provided to us that way, so that they can discuss with us and show us at the same time. Is that something that's possible, Fedor?
Yes, it wouldn't be a problem. We can do it.
Yeah, excellent. Yeah, so so yeah, in terms of like the second challenge, we'd like to basically just see what you found out. However you want to present that is kind of up to you. But yeah, some sort of slideshow, a couple of slides, and then if you find out anything particularly interesting, just talk through what you found and we'll have a look at what you present. I hope that answers some sort of way.
Okay, I think that's probably it then in that case. Thank you all for coming. And yeah, good luck with the challenges.